everyone. I am Mercy Pratheeba, Assistant Professor of Computer Science, A.D.M. College for Women, Autonomous, Nagapattinam. Today my topic is Software Engineering. In this topic, Part 1 provides some background and introductory information on software engineering. This part of seminar provides a brief history of software engineering, statistics demonstrating common problems with software development, and definitions for the term software engineering. Additional definitions for different software engineering terms will be provided throughout the presentation. And in part 2 presents software engineering concepts, the principles, methodologies and techniques, life cycle methodologies. The first electronic digital computer was the electronic numerical integrator and calculator, which was built for the US Army in 1946. Downing, Douglas and Michael Covington, Dictionary of Computer Terms, New York, Barrington Educational Series. High-order computer programming languages started to come into being in late 1950s. Eventually, some training on how to write programs was developed. However, the training available at the time was not advanced enough to provide the methods and techniques needed to develop large systems that were reliable, delivered on schedule and within budget. As it turned out, we were not very good at building large systems on time and without overruns. Digital computers were less than a quarter of a century old, and already we were facing a software crisis. The crisis came about not only because the software being produced did not function properly, but because of the problems associated with how we developed software and the growing demand for more software than the industry could provide. The software crisis is characteristic by many problems: the lack of defined requirements and the constant changes to requirements that are known. Scheduled and cost estimates are often grossly inaccurate. The productivity of software developers hasn't kept pace with the demand for their service, and the quality of software is sometimes less than the adequate. Some of the basic problems pointed out at the 1968 NATO conference have continued. Progress has been spotty where improvements have occurred. Much of them can be attributed to software engineering practices. Software engineering enables the manager to control the process of software development and provides the software developer with a foundation for building high quality software in a productive manner. This part of the seminar will focus on the following software engineering concepts and how they relate to one another: the principles of software engineering, the methods and techniques used to develop software, the methods and techniques used to manage software development, how these methods and techniques are combined into a life cycle methodology, how software engineering processes and procedures are defined for specific organizations by tailoring the above mentioned methods and techniques, and finally how these methods and techniques are supported with automated tools. This figure shows the relationship between software engineering principles, methods and techniques, life cycles. Each layer in the figure is built on the layer below it, and the outermost layer are more susceptible to change over time. Principles are the basic of all methods, techniques, life cycles, processes and tools. The first three layers are in the realm of theory. The final two layers are physical applications of the theory and concepts of software engineering. Software engineering principles are more important than any particular methodology for building software. They enable the software engineering to evaluate various methodologies and apply them when they are appropriate. The following are only a few of the software engineering principles recognized today. Software development is a creative activity. There is a tendency in any creative processes to neither precise nor accurate, but rather to follow the inspiration of the moment. Rigor is a necessary complement to creativity in every engineering activity. It is only through a rigorous approach that we can produce more reliable products, control their cost, and increase our confidence in their reliability. Various degrees of rigor can be achieved. The highest degree is what we call formality. In every engineering field, the development process proceeds as a sequence of well-defined, precisely stated steps. In each step, the engineer follows some method or applies some mathematical technique. These well-defined methods and techniques applied in a rigorous and systematic approach can be uniformly applied and taught. The amount of rigor and formality depend on the task at hand. A complex system may be divided into separate and distinct pieces called modules. Modularity is an important property of most engineering processes and products. For example, in the automobile industry, the construction of cars proceeds by assembling parts that are designed and built separately. Furthermore, parts are often reused from model to model, perhaps after minor changes. Abstraction is a process in which we identify the important aspects of a problem and ignore its unimportant details. A useful abstraction for the owner of a car is the owner's manual, which describes the various features and operations of the car. For the person maintaining the car, a useful abstraction is the maintenance manual. Other abstractions include activities conducted in the factory needed to design and build the car. Anticipation of change is the process of creating software so it may be easily modified. After software is released, based on feedback from the user, the application must evolve as new requirements are discovered or old requirements are updated. If we can anticipate the change of context in which a software component might be embedded, we may then design the component in a way that such changes may be easier to implement. The principle of generality may be stated as follows. Every time you ask to solve a problem, try to focus on the discovery of a more general problem that may be hidden behind the problem at hand. The success of such tools as spreadsheet, database, and word processor is that they are general enough to cover the practical needs of most people when they wish to handle their personal business with the computer. If the problem at hand may be restated as an instance of the problem solved by general package, it may be convenient to adopt the package instead of implementing a specialized solution. In the early days of automobile technology, it was possible to customize cars according to the specific requirement of the customer. Nowadays, it is not possible to ask for personal car design unless one is ready to pay an enormous amount of money. Incrementality means that the desired application is produced as an outcome of an evolutionary process. One way of applying the incrementality principle consists of identifying useful subset of a software application that may be developed and delivered to customer in order to get early feedback. We progressively add functions to the applications being developed, starting from a kernel of functions that would still make the system useful, although incomplete. We have just finished going over software engineering principles. We will now discuss software engineering methods and techniques. This has been further split into discussions of development methods and techniques and management methods and techniques. This basic flow can be used for virtually all problem-solving activities. This process flow was initially modeled for manufacturing and applied to systems engineering and then to software engineering. The first step is to decide what is to be done. Once the objectives have been determined, we next must decide how to achieve them. This is followed by a step in which we do it. Whatever it was determined to be, then we must test the result to see if we have accomplished our objectives. Finally, we use what we have done. The same process can be used in building anything. Using a car as an example, First, we decide on what the car should look like and detail how it should be built. The car is then built, tested and used. Software engineering follows the same types of activities. This chart restates the basic problem solving flow to software development methods and techniques. Systems engineering and requirement analysis is the what, design is the how, the implementation is the do and testing, and integration is the test. During product use, maintenance may be required. The software engineering principles reviewed earlier are incorporated into various software engineering methods and techniques. The principle of rigor and formality will require an adoption of appropriate methods to define requirements and design the system. Modularity, abstraction and generality will be applied to tame the complexity of the design and make sure the design is understandable. Finally, anticipation of change and incrementality allow the designing of systems that can easily evolve. Software engineering methods provide the technical how-tos for building software. Each one of these software development activities will be defined in the slides to follow with the steps in each activity specified and shown with the sample techniques. Wind tunnels, aeronautic simulators and space flight instruments are examples of types of applications that probably need to implement each of these development activities. However, your application area may only require a subset of these development activities. System engineering is an application of scientific and engineering methods to transform user needs into a description of the system that will fill those needs. Software engineers need to be intimately involved in software engineering efforts to provide software expertise and assist in evaluating design decisions. Trade studies are performed and alternatives are evolved to determine the most appropriate system design and allocation of system requirements to hardware and software. Finally, the system requirements are separated and allocated to hardware-related requirements and software-related requirements. The software engineer helps determine what requirements are appropriate to implement in software. Items such as the digital dashboard display, engine and control systems like timing, fuel injection and emission control are all controlled by software. The software engineering process starts during the system engineering phase. Software requirement analysis is the process of studying the system requirements allocated to software to arrive at the definition of a software requirements. The requirements that were allocated to software are now analyzed and expanded in the software requirement document. The software requirements are checked for clarity, completeness, consistency, testability, etc. For example, if one of the requirements for a car's computing system was for it to be user-friendly, this requirement is subjective, ambiguous, and untestable. Further investigation would be required to see how car owners define user-friendly. Perhaps this would include full words on the buttons instead of acronym or icons. Any problems discovered during the review or formal inspection of the software requirements document would be recorded in a trouble report and corrective actions would be performed before the requirements are considered complete. This list shows a small subset of questions asked during the formal inspection of the software requirement documents. Software implementation is the process of translating design and data definitions into the form of a programming language. The programmer reviews the design for possible reuse components, then translate the design into programming language source code. This source code is compiled and linked into a load module. The module is loaded onto the processor and the program is run. Errors are identified and fixed. At this point, without our car, the software for the single module, let's say for the fuel injection system, would be loaded on a test computer mounted on the top of the engine and run. This software component is verified to ensure the engine will start, run and perform as expected. Testing is the process of operating a system or component under specified condition, observing or recording the results and making an evaluation of some aspects of the system or component. Testing should be performed by someone other than the developer. Testing begins with test plans and procedures being produced. The test plan provides managers and test personnel with the necessary approach to validate that the coded module perform correctly and that the requirements of the system have been satisfied. The test procedure documents specify the required operator action and the input and output for each software test. Errors found based on the testing evaluation are sent back to the programmers to debug, and metrics are kept on the number and types of errors so that defect analysis can be conducted to determine the root cause for the errors, so as to prevent them in the future. On our car, at this point, the fuel injection, emission control and timing system would be brought together, loaded on the test computer and the complete engine component tested. Integration is the process of combining software and hardware components into an overall system. This phase takes the tested hardware component and software component and installs them into an integrated system. An acceptance test is conducted to validate that the system meets the user requirements. The same kind of trouble report used for testing can be used during the integration phase in case problems are found. At this point, the fuel injection, emission control and timing system are loaded into actual computer hardware box that will be installed in the car. All tested components are brought together and tested together as a system. This is the first time that engineers can physically climb into the car and test drive it. Maintenance is process of modifying a software system or components after delivery to correct faults, improve performance or other attributes, or adapt to a changed environment. Maintenance is the set of activities that are performed after the system is delivered to the customer. Basically, maintenance consists of correcting any remaining errors in the system, adapting the application to changes in the environment, and improving, changing or adding features and qualities to the application. With our car example, maintenance would be performed when the owner decides he wants additional option to work out new car bugs or to equip cars with catalytic converters so that they meet US environment standards. The highlighted activities in the chart represent the software engineering management activities that span across each phase of development. Each one of these activities will be defined in the slides to follow and shown with an example technique. Project schedule are one of the management plan component and are typically displayed in a Gantt chart as shown. The tasks listed in the Gantt chart are based on the development activities described earlier in this talk. Plans are one of the major inputs to the project tracking and oversight process shown next. Quality assurance assures that the product conforms to required standard and that the proper procedure are being followed in the development of products. Actual product like computer code or design documents are looked at during product review. The product is compared to written standard to ensure adherence to them. Errors are reported to management for resolution. Process reviews are used to review the record and other documentary evidence to verify completeness of the process and that the organization's defined procedures were followed. We will now discuss life cycle methodologies, which organize methods and techniques into an ordered sequence of an event. Life cycle model provides engineered approach that can be used to structure the software development process. These models are a convenient and idealized picture of the process we follow to build, deliver and evolve software systems. Software lifecycle model typically include phases that correspond to these development activities. The primary difference in the lifecycle models is the sequence of and emphasis on these activities. Waterfall was the first formal life cycle, Within the waterfall methodology, each phase is completed before the next is started. Each phase produces products that are used in the next phase. It was developed in the early 70s when projects were simpler and smaller in scope. It ran into problems with larger products where all the requirements were not known prior to design or the requirements changed frequently. This life cycle methodology is appropriate only for small projects whose requirements are well documented and understood. The incremental life cycle is an adaptation of the waterfall model. This life cycle methodology is used for more complicated systems and systems where all the requirements are not known upfront. It breaks large products into series of smaller deliverables called builds. In the later builds, requirements can be added based on customer feedback on the earlier builds. It also provides the opportunity to deliver limited functionality early in the project. This life cycle is driven by risk management. It recognizes that may be many uncertainties in the project and works to reduce the probability of negative impacts due to those uncertainties. Risk analysis is performed to identify, analysis and rank risk. Risk mitigation identify actions to be taken to reduce the amount of risk, revolving risk through planned corrective actions, and monitoring the situation to see if the corrective actions removed or reduce the risk as planned. The spiral life cycle is a further refinement of the basic waterfall model and was first published in 1988. The figure shows a model that consists of series of learning cycles that begin with defining the objectives and then performing a risk assessment to identify areas of greatest uncertainty in the project. The number of iterations through the cycle varies based on the uncertainty of the problem. Simple problems take one pass and look very much like a standard waterfall life cycle. More complicated problems may involve several phases through the cycle to resolve uncertainty to an acceptable level. Thank you. We'll see in the next class.